Hi, in this class we will be discussing about the arc welding. See, mainly this arc welding consists of a minimum these 5 elements. They are called as, this is the concept of thermionic emission, then the power sources, then the Lorenz forces, then the continuation to this Lorenz forces itself, that is arc welding process. Then this is also same thing. Then heat generation at cathode and anode, then temperature. Apart from this, there are so many other things like electrical configuration, all those things, but all these things are just only details. Then even more further, so in the continuation to this video, what we will do is, we will do some calculations of this arc welding also, but in this video we will be confining to our explanation only to the electrical configuration itself. Okay. So now let us dive into these points here, that is the concept of thermionic emission. Okay. Before going to understand what is this concept of thermionic emission, first of all what we have to understand is that here we need to understand a electrical configuration of this any arc welding process. Okay. Now let us try to understand these configurations here. You see, normally according to our understanding of this electrical configuration here, so what we do is, we would consider something from something called as a power source. Okay. So this is some power source. Okay. So from the power source what we do is, we would give connection this from a power source here, so from this power source so what we do is, we would take these connections okay. So what is this connection is, say let us say this connection is something like positive, right. So yeah, this is like a this is positive, this is negative. Okay. So this I am going to call it as a power source. Okay. So I am not going to let this one say with a subscript which is called as a PS. You can also say this as a PS, but there is something called as a, in welding we have two concepts here, which is called as a primary source and a second source. So you will be confusing there. So that's the reason why I am labeling each and every names here. Please keep this point in mind. Now what we will do is, we will be saying here that is a connection here, we will give this connection here from power source here, and the same power source from top to the bottom, okay, without any change here. Okay. This having given here this connection something like this. Okay. So here we are taking this power source here, okay. Then one end of the terminal is connected to a base plate like this. Okay. And other end of the terminal is connected here. Okay. This is a simple configuration. This one is called as a simple configuration, and at the end of this session, if you look at this configuration here, so what I am trying to do is, so if you look at this base configuration here, so we need to use the same configuration here again. So what we can do is, we can copy the same thing here, same powers, same thing we are going to put it here in the 3 cases here. Okay. So just alignment change here. So everything is same. Okay. Here at most you can make 3 configurations. They are called as here, that is if we give positive terminal to the electrode, and a negative terminal to the workpiece, this is a workpiece and that is the electrode, and a negative terminal to the workpiece or work material. Okay. Then this type of configuration is called as what we can say is that here direct current DC RP. Okay. So what is this DC RP means? Direct current reverse polarity. Reverse polarity, direct current reverse polarity. Okay. Now the same thing what we do is, if we do this in a alternate fashion, I will do it here in a alternate fashion, right. So then this is called as direct current straight polarity. Okay. So this is a negative and this positive, right. So rest of the things are same. So what are the rest of the things are same is here, here is the electrode, and here is the workpiece. Here is the workpiece. Okay. So if we give this connection here, alternatively back, so if you give this reverse one, so actually the electrode connection given to the negative terminal of the from the power source is called as a direct current straight polarity. If we reverse it, it is called as a direct current reverse polarity. Okay. So always ensure that normally, so electrode in the sense that we generally ensure that we give connection to the negative terminal, but we can give the positive terminal also. So depending upon the cases here. So if we give the connection electrode to the positive terminal, it is called as a direct current reverse polarity. This is called as a direct current straight polarity. Okay. So we will be looking at it what is going to be differences here, but in between this direct current straight polarity and direct current reverse polarity, so we have another option called as that is direct current is where we are dealing here, but there is another option called as a alternating current, right. So alternating current high frequency, that is also one option is there. So, alternating current high frequency. Alternating current high frequency, this is also one option is there. So, what happens in this alternating current high frequency is that here, so the frequency is based upon the inverse of time, right. So, here for every second here, say 1 second, first it will be positive, then it will be negative, then it will be negative and so on, okay. So, when this one is negative, this is going to be positive, then negative, then positive and so on like this, okay. So, continuously it will be there like this, okay. So, for this what we need to do is we need to understand based upon time here. So, to understand based upon time here, so what we need to do is we need to look at this case separately here. So, we can't look at this in a combined fashion. So, what I am trying to do is I am trying to take only this picture here for understanding. When there is something called as a alternating current, as I said here, that is based upon frequency, right. So, what we have to do is we need to know what is the frequency, okay. Normally in India, if you look at normally any cases where generally if you look at the cell phone adapter or anything, you can easily observe the frequency here is 50 hertz. So, for example, if you look at something like USA, UK, etc., you will see some adapters, you will see that is actually work for 60 hertz. Okay. So, what is this basic meaning is here is that here we know that frequency is a inverse of time, right. So, this is the frequency and this is the frequency. So, if you look at the time here, 1 by frequency you can observe here. So, 1 by 50, okay. So, what is this meaning is 0.02 seconds. So, for here every 0.2 seconds, this voltage versus time here, okay, time. So, time is in tau here, okay. Say if it is a voltage or current which is in amps, okay. So, whatever it is here, you will observe here that for every 0.02 seconds, here. So, for every 0.02 seconds here, what happens is the frequency will change. This frequency, the polarity is going to change. So, no, this will be totally right, one, right. So, yeah. So, here for every 0.01 second, this one frequency is there, hey, one frequency. So, hence this is half frequency. So, one frequency is going to complete for 0.02 seconds, like so every 0.01 second this polarity is going to change. So, that is where our focus of interest here, okay. So, every time what happens is that the terminal will be changing its polarity, terminal will be continuously changing its polarity. So, that is actually this is logic here, okay. Now, come to the point here to understand here. Now, this is a direct current straight polarity, there is a direct alternating current high frequency, and this one is a direct current reverse polarity. So, keeping these things in mind, if you look at the power sources here, so power sources, so this is actually the power source which we discussed here, right. So, when you look at this, this is power source has been discussed here. So, the power source can be two varieties, right. Yeah, I would like to give it, the power source can be two varieties, that is power source here is only one thing, that is current here. Okay. So, the current can be two varieties, not a direct, so we can actually reduce this one here in a single fashion. This is it can be a alternating current, then there can be a direct current. So, the direct current also can be categorized into two varieties, that is a direct current straight polarity, direct current reverse polarity. That is what we discussed in the previous class, right. So, it can be AC or DC. So, on AC, if you are using only alternating current, you have option, only one option, that is a alternating current, high frequency only we have to use. So, there is no any other option here. So, these are the concepts regarding the power source here. Now, this is where actually the concept here, that is in welding, whenever we are using current for welding operation, so the Lorenz forces will come into picture, especially in case of a arc welding. Why these Lorenz forces are going to come in picture is that here we have a concept called as here, that is a magnetic forces also there. Okay. Why there develops magnetic forces is that here, first of all, you need to understand, before going to understand Lorenz forces, first of all you need to understand what is a Lorenz forces. Among the Lorenz forces itself, there is a glitch which is called as a Lorenz magnetic forces here. Okay. So, before going to understand Lorenz forces, all those things in detail, first of all what you have to do is, you need to understand a simple concept, that is called as a, what do you mean by a magnetism, simple definition. Okay. So, for simple understanding, what I am trying to do is, I am trying to explain here with a small atomistic level model here. So, what is this model is that here, say for example, there is a atom. Okay. Let us say this atom is a hydrogen molecule, Okay. So, this hydrogen molecule has the central axis, right, central axis is there. Okay. So, what I am trying to do is, I am trying to put this one in a, somewhere like this. So, this is central axis is there. Okay. Now, this okay, this not this way, there is some nucleus is also there inside. Okay. So, let us say this nucleus has one proton, okay, one neutron, then outside there is something called as a one electron. Okay, one electron is there here. Okay. You see, the one proton is also a positive charge, and one electron is also a positive, some charge, some negative charge, right. If you look at this normal simple understanding, what I am saying is very, very simple understanding. According to magnetism, whenever a charged particle makes a displacement then they produce magnetic field surrounding to it. Field surrounding to it. So, this is a basic simple definition for you to understand. Okay. So, more than this simpleness it is not possible here. Okay. So, whenever there is a charged particle and they make a displacement, then they produce a magnetic field surrounding to it. So, now look at the concept here. here what is happening is that here this electron is a charged particle, right. So, this electron is making a displacement like this, right. So, which we call it as a spin, right, spin magnetic moment, okay. And at the same time this electron is not just only spinning about its own axis, right, it is also revolving around the central nucleus, right. So, it is going also here in this fashion, okay, that is called as a spin magnetic moment. Then we can call it as a radial magnetic moment, radial magnetic moment. This is also there, okay. Spin magnetic moment is there, though the spin magnetic moment is represented with ms, the radial magnetic moment is represented with a mr, m subscript r here, okay. So, as a net result what will happen is that here you will observe here on the central axis, here on the hydrogen atom. So, the net effect is being applied. So, how this net effect being is applied is that here. So, then we can call this one as a m net, the magnetic moment net at the central axis is equal to magnetic moment ms plus this one which is called as a mr, okay. So, for convenience sake I would like to differentiate this with a different notation here. It is not that bad, okay. So, something like this is not, no, even there is no change here, no drastic change here, something like this, okay. So, now you would observe here that the net magnetic moment, this is the net magnetic moment is equal to here, and the spin magnetic moment is about this one, right. So, this is the spin magnetic moment that we were talking about, okay. So, okay, that is a net magnetic moment here and spin magnetic moment is here, okay. This is for just only hydrogen, where the hydrogen has one electron in its outermost shell and one proton in its innermost shell, okay. So, the net magnetic moment for this value is this much, okay. This is a normal simple definition of a magnetism. Now, what we will do is we will use this the same logic for normally any other examples, okay. So, we may not be in a general we will be using most of the time iron, aluminum, right. What I will do is I will explain here another case here, another case. So, the another case is here helium, another case here is helium, okay. So, for helium what will happen is that here there are two electrons in its outermost shell, 2 electrons, 2 protons and 2 neutrons, right. So, I am going to take a not exactly value exact isotope, I am going to take whichever the isotope I am interested in. So, for this, okay. So, I have taken this isotope, so please do not lose your brains here, okay. Yeah, in this helium 2 protons, 2 neutrons in central atom and 1 electron is there here in this direction, right. So, there would be another electron here in this fashion, right. So, here in this fashion when it is there here, this electron is this is the second electron, no. So, this second electron what it does is, this is the number 2, not a number 2 electron, this is a 1 electron here. So, this spins in opposite direction, okay. At the same time they revolve in opposite direction, they revolve in a different direction here. Okay. So, this is a different direction. So, this direction is what we are going to talk about here now in this case. Okay. So, one electron is spinning in one direction, another electron is spinning in another direction. So, as a net result what will happen is that here this here ms for first electron minus ms for second electron, they get cancelled out, plus m r for first electron minus m r for second electron, they get cancelled out. Okay. So, just have a look at here, just have a look at this logics here. These two gets cancelled out. So, these two gets cancelled out, these two get cancelled out, right. So, these two get cancelled out. These two get cancelled out, right. So, you will observe here this electron will get cancelled out. So, as a net result, this m net is equal to 0. So, for helium there is no magnetic moment, but for a hydrogen you can have a small quantity of a magnetic moment. Okay. Now, if you look at this further, we are interested in not all these things, right. We are interested in our engineering materials. So, our engineering materials usually are iron, aluminum, nickel alloys, right, chromium alloys, right, etc., right. So, for all these things we need to look at what is this net magnetic moments. Okay. So, this net magnetic moment we need to look at what are the free electrons in its outermost shell. Okay. So, what are the free electrons? How many free electrons are there here in its outermost shell? That will actually decide this the magnetic field of a material. If you look at this iron, so iron has more number of free electrons in its outermost shell. So, that is a basic reason why iron will deflect to the magnetic field. Okay. So, that is the reason why iron can have the magnetism contained inside it, that is the basic reason. Now, after understanding this magnetism, now we will dive into the concept called as a, what is this concept? What are the Lorenz forces here? Okay. So, what do you mean by this Lorenz forces is that here, first of all, this understanding of this basic connection we will try to understand first, okay, then we will dive into the Lorenz forces here. Here what we will try to do is, we will try to take one basic definition here, one basic configuration, right. So, the basic configuration is here, which is a direct current reverse polarity. I would like to use it. So, this direct current reverse polarity. Okay. Now, considering this direct current reverse polarity, we need to even more use it like this. Okay. So, direct current reverse polarity here. In a direct current reverse polarity, we have given positive terminal to the electrode and negative terminal to the workpiece. Okay. So, here I would like to write very with boldface, positive terminal to the electrode and negative terminal to the workpiece. So, in order to welding to happen, first of all what we need to do is, we need to understand the concept of how this welding is going to happen, which is called as through a physics point of view, which is called as a thermionic emission. When you look at this thermionic emission here, that is here, yeah, you see this connection is there, right. this connection at a very first time, it is not, when you give just a connection, the welding is not going to happen. As just by giving just a connection, the welding is not going to happen. So when this welding is going to happen is that here, we need to give first connections here. Then what we need to do is, we need to take this one here, which is like this, just like this. Okay. In a 3 steps we need to play. We need to do it in a 3 steps. What are those 3 steps? So first step is giving connection. First step is giving connection. Okay. Then the second step is like this. The second step is where we need to close the connection, or we can call it as a closing the loop. So how we are going to close the loop is, we are going to bring down this electrode here, okay, or else we can call it as a join the connection, so that the circuit is complete. Okay, close the circuit. This is the condition. Okay. So first of all, it is in a open circuit. So when in the first step it is a open circuit. Now what you are going to do is, you are going to close the circuit here. So this is the workpiece and this is the electrode here. So by just, this is connected to one terminal and this is connected to other terminal. So by just closing the circuit, what will happen is that you are going to join these connections. So as a result, what will happen is that here you will observe that there is a tremendous amount of electrons will be continuously moving in a circular fashion here from one side to other side. So from the power source, continuously the electrons will be going on from here. Okay. Now what you should do is, you should slowly, very slowly, you have to, this is the first circuit, right? So join the circuit like this, then slowly, I am going to write it here, please. Slowly remove the electrode, from the workpiece. This is very important. You have to slowly remove this electrode from the workpiece, so that what will happen is that here this welding can happen. So this is the primary requirement. If you do this process, then the thermionic emission can take place. If you don't do this one, the welding will never happen. Please keep this point in mind. Once again I am saying this. First of all, in order to happen a welding, in order to start the welding, first what we have to do is, we have to give connections to the, from one terminal to the electrode, one terminal to the workpiece. Then what we have to do, we have to close the circuit. So when you close the circuit, naturally the power source is on. So continuously the electrons will be moving away from one post to other post. Then what will happen is that here, these electrons, when they are continuously moving here, you are trying to slowly remove away this electrode from the workpiece. Slowly, you should not do it very fastly, you have to do it, that's what I am said here. The very important factor, which is called as a slowly. Okay. So slowly you should try to remove it. Once you try to do this one, then the concept of thermionic emission will take place here. What do you mean by the concept of thermionic emission? So what is the concept of thermionic emission is that here, the continuous impingement of electron on the charged surfaces. Charged surfaces that takes place and this impingement causes severe thermal rise in the surfaces is called thermionic emission. Thermionic emission. So what will happen is that here in this surface, when we close the circuit and then slowly unremove it, what will happen here? That is where we are going to discuss in detail according to the definition. Okay. So what will happen here is that here, just have a look at these circuits and all those things. So first I am trying to take this only two portions here. So first what is going to happen is that we are going to close the circuit, right? Once you close the circuit, then this continuously whatever these 2 points are there here, these 2 objects I am going to expand here and then try to explain here for you. So just to have a look at here. So these 2 are the electron and this electrode and the workpiece, right? This is the electrode and the workpiece. So here in this electrode and workpiece, what happens is that here, first what we have done is we have closed the circuit, right? So when you close the circuit, this electron connection is there, right? So the electrons will be going away from one point to here, this point, okay? So once this once you close the circuit, electrons are continuously going here, then what you are going to do is, you are going to stop this going here from one point to other point, so that you are trying to bring it back here, okay? So when you are trying to bring it back, close the circuit here, close the circuit, right? Here also the electrons are going downwards, okay? So first what we have done, the first case is here we are trying to close the circuit, so this is the first case. Then what we have done, we closed the circuit. Then what we have done is, we are trying to take away this circuit from this side, okay? So first we closed it, we are trying to bring it, we closed it, then again we are going to take away this one away from it, okay? What will happen this time is that here, when you close the circuit, the electrons have been closed, right? So the electrons will be continuously moving. But when you slowly unremove it, what will happen is that here, the tendency of the electron movement from either anything, okay? Here in this case, this is going to be anodic surface. So this is going to be anodic surface or cathodic surface. So it can be any case, okay, cathodic surface or anodic surface, surface to other charged surface. Will still remain. That's where this is a problem, okay. So that will still be remained, okay. So even if you unremove it, what will happen is that here the electron will be tendency will be still going on. So naturally what will happen is that here the electron here will come out from this place and then try to impinge on the other charged surface, whether it is a cathodic surface or whether it is an anodic surface. Here we are confining our idea to thinking that here, just taking an assumption that the electrons are always coming from an electrode to the workpiece, okay. So now when the electron is coming out from this workpiece, naturally when it is coming out, this electron is in a free state, it is in open atmosphere, right. So what will happen is that here the electron will come here and then it will impinge here, impinge on this surface. Then what will happen is that here this is the electron, no, here what we are trying to do is, say for example here I will remove this one and then put a positive charge here, negative, and this is positive charge, okay. So naturally this will have a positive charge, this will have a positive charge, this will have a positive charge, right. So naturally what will happen is that here sometimes it will come and attach here, but you can see the mass of the electron is a much lesser than mass of any atom, okay. Or else what I can do is I can close this one also like this, not just like this, okay. I can close this one. You can take this condition for anything, not only for this, you can take this condition for anything, okay. So this is a positive charge and this is a negative charge, so you can use it for any configuration, please. And here the mass of an electron here which is coming here is already there is a electron negative charge is present here, already there is negative charge is present, already there is negative charge is present. So like poles will repel each other, opposite poles will attract each other, right. So normally these like charges will, what will happen, they oppose each other and opposite charges will attract each other, right. So now what will happen here is that here this is also a negative charge, that electron is also negative charge, so it will go away from here, from the workpiece, okay. Like this what will happen is that here the electrons which are coming out again go and touch the surface, and continuously there the electrons are also impinged, they are also oozing out from the cathode here, which is a electrode. Now what will happen is that here, because of this continuously one side electrons are coming out and on the other side these electrons are being pushed away from the positive, this negative charge. So this electron will have no other place, then what this electron has to do is that here these electrons, these electrons here which are coming out here, okay. So keeping these points in mind here, all these points in mind, okay. So these electrons which are coming out here, just I'll keep some proper place here for the approximate center, okay. So the electron that is coming out here, electron is going to come out and then electron is going up, electron is coming out and electron is going up, okay. Electron is coming out and electron is going up. So like this what will happen is that here this impingement is going to take place. What is this called as a continuous impingement. Continuous impingement of electron on charged surface. Takes place. So as a result what will happen is that here the thermionic emission will take place. When a thermionic emission takes place means the electron, what is actually happening here is that here, look at here, just a simple, for you simple idea here, there is one atom here, okay, and so there is another atom here, okay. So this atom is here, yeah, see there is a atom here, okay, and there is a atom here, okay, and there is very small electron here, small electron, okay. So what this small electron doing is, it is coming and hitting here and then going up, it is coming and hitting here and going up, okay. So continuously it is coming and hitting up and going up like this. So naturally what happens is that here like this, naturally what happens is that a thermionic emission will take place. Because of this thermionic emission, so because of this thermionic emission, the temperature will rise to 5000 degrees centigrade. The temperature will rise to almost around 5000 degrees centigrade. So because of this temperature rise to 5000 degrees centigrade, we will use this heat for melting of the workpiece and for joining. So this is the concept regarding this, the thermionic emission. So just to have a look at here, the basic definition here. The basic definition here is that here, the basic definition here is the continuous impingement of electron on the charged surface that takes place in this impingement that causes severe thermal rise in the surfaces, and this is called as a thermionic emission. So this is one definition, and the process of this definition. So I explained here how this emission also everything is going to take place, right. So now if we have a look at here, just to have a look at here, that is a Lorenz force. This we are talking about Lorenz forces, right. We already had a discussion about magnetism concept, right. Now we are talking about electrons also, right. So we understood just now based on definition, thermionic emission, the electrons are making a displacement, right. The electrons are moving from one point to other point. Now we already said a definition, right, regarding this magnetism. What is the magnetism concept here? That is, whenever a charged particle makes a displacement, they produce a magnetic field surrounding to it. So this Lorenz was the first person to identify what is actually happening in the welding pool, where when this cathodic surface is coming and touching this anodic surface, it is not just only the electrons that are going to move here, but as a result what happens is that here there is a Joule heat effect is there, then there is a convection heat transfer is going to take place, then there are something called as a different concepts here, that is called as a Marangoni plus a gas drag force, all those things are also there. But main thing is that here there is something called as a Lorenz forces. What is this Lorenz forces is that here the electrons are moving making a displacement, so as a result this causes a magnetism, okay. And also there is a liquid pool, so completely the temperature rise is there here, this is the first point, right. The second point is there is a temperature rise. So when there is a temperature rise is there here, the temperature rise is around 5000 degrees centigrade. At this temperature all materials, any material will melt in the nature, okay. So everything will melt. So the material is in the form of is converted, whatever the solid is there, the solid is directly converting into a liquid. Now this magnetic force is there, right. So the electron impingement is also going to take place, right. So now as a result what will happen is that here the plasma is going to develop here. When the plasma is going to develop here, these forces are uneven or unbalanced forces. So what the Lorenz force says is that here, if we maintain a proper connection and proper movement of this, and the Lorenz forces are being in a proper place and tallied here, so the welding will happen without any spatter. Otherwise what will happen is that here you can observe the liquid droplet is going to come out here, and then you can actually observe here liquid droplet which is coming out here, and the convection heat transfer is going to take place, conduction heat transfer is going to take place, radiation also is going to take place. So, all those things when they are going to take place, you will observe here that because of the magnetic forces and all these things, the heat dissipation is not going to take place in a proper way. The heat dissipation is going to take place, this magnetic influence is going to take place, magnetic flux or something is going to influence here. Because of this, the liquid molten metal will spill away from the weld pool. So, when it spills away from the weld pool, you will not be able to produce a proper welding process. So, for this reason what we need to do is, we need to we need to balance the Lorenz forces. To balance the Lorenz forces, what we need to do is, as I said just before, the magnetism concepts and all those things, what we have to do is, we need to look at this concept called as the balance of magnetic forces. So, to balance this magnetic forces, obviously what we need to do is, whatever the magnetic force is there, we need to maintain with a centrifugal force, and then, so that is the reason why what we do is, we have to weld the material in a certain fashion, maybe like this, right. So, or maybe zigzag manner, right. So, in different shapes and different directions we will be managing. So, we have to manage the force along with the mechanical force. So, the mechanical force is the centripetal force, this is a mechanical force. So, whatever the torch that you are going to, you have only one option. So, the torch movement is the only option that you have. So, with the torch movement you have to maintain this magnetic forces and then make this force equivalent here. So, that is where the crux of the problem here in case of this arc welding. So, if for that reason what we will do is, you need to take a special training for arc welding. Directly you cannot go and do a arc welding process. And also one more point here is that here we were talking about several times regarding the temperature here. The temperature is 5000 degrees centigrade. So, at this 5000 degrees centigrade, what will happen is that here all the X-rays, gamma rays, everything is going to emit. Okay. So, at this temperature almost the matter is going to convert into energy. So, what we have to do is, we have to be very careful, because this is very harmful to human eye. So, that is the reason why whenever you just have a look at the arc welding through a naked eye, you will get a within just, if you have a do this just look at just only 5 seconds, that is enough for your eye itching for the complete day. If you are doing this normally in a regular basis, so you will lose your sight here. So, always we have to ensure that whenever you are using this arc welding, we need to wear the goggles and special goggles, and also we need to take a filters, all those things, where polarized glasses also we have to be ensured, and then we need to use those ensured glasses only, okay, not any cheap quality. One more point is that here, please remember, if we look at the X-rays or gamma rays for 3 to 5 seconds, that day completely eye itching will be there. Please keep this point in mind. Now, one more point is that here, one more point, the balancing of the forces, right. So, this is also we discussed just before. Coming to these concepts regarding this heat generation at cathode and anode. What is the amount of heat is generated at cathode? What is the amount of heat is generated at anode here? So, always the cathode emits the electrons. So, hence what happens is that here the heat generation here is very high, which is called as a 2/3 of the heat is going to generate here itself, whereas the anode is not going to emit anything. So, it is going to produce only the ions, okay. So, as a result 1/3 of the heat is going to generate here. So, that is the only logic here, there is no any other differences here. So, overall the total heat is around 5000 degrees centigrade, okay, right. So, this is the only difference you can actually differentiate from one over the other. Now, coming to the next point here, which is called as the temperature and all other aspects here. The temperature, as I said, it is 5000 degrees centigrade, but we need to remember one concept here regarding this same case, okay. You might ask a doubt that what is the basic differences between this direct current straight polarity and direct current reverse polarity, and what is the basic differences between these two things, right? So what is the difference between direct current straight polarity, direct current reverse polarity, and direct current so whatever this alternating current, high frequency, all those things here, if we just have a look at here, yeah, I think I can use this one, yeah, yes. So direct current straight polarity, direct current reverse polarity, and a alternating current high frequency. What is the basic differences between all these three things is that here, just to have a look at the differentiation that I am going to give based upon a simple diagram with a weld pool. Okay. See, if you have a look at here, this diagram, just have a look at this diagram. So this diagram is like this, right? The direct current straight polarity, direct current reverse polarity, and a direct alternating current high frequency, isn't it? So for this, you can see here, yeah. So you can see here in this case, this is a direct current DCSP, ACHF, and then DCRP. Here, if you consider this weld pool, if you consider the weld pool, okay, I am going to draw this weld pool. So the same color only I am going to use it here. So if you look at the weld pool, in each cases, if you look at the weld pool in each cases, here, and here, and here, okay. So just to have a look at this diagram, okay. In a direct current straight polarity, you will observe that here the weld pool will be like this. Will be like this. Okay. So the diameter is we can call as a diameter of DCSP and the height of DCSP. Okay. So likewise here, if you look at this diagram, the diameter of this one and the height of this one. This is called as a diameter of DCRP, and this is the height of DCRP. Okay. And if you look at this alternating current high frequency, so they would go like this. Okay. So this is the diameter of ACHF, and this is the height of ACHF. Okay. I would like to summarize here the diameter here, the weld pool diameter. Okay, we can call it as a weld pool diameter. Weld pool diameter is, so this D of DCSP is less than D of ACHF is less than of D of DCRP. Okay. Likewise here, the H of DCSP is greater than the H of ACHF is greater than the H of DCRP. So this is the case. Okay. So the only difference is that here remember when we use this direct current reverse polarity, we cannot weld more depth, okay. We can weld a high thermal conductivity materials can be welded here, okay. The thermal conductivity material which are very high, that can be welded here. Whereas the direct current straight polarity, you can weld the high thickness materials. So the thickness materials, high thickness materials can be welded here. So medium is, we will go for alternating current high frequency. So if the material has high thermal conductivity, we have no other option other than to go for DCRP, and in a DCRP, remember, we cannot go for high thickness, okay. The thickness is very less here, the thickness is very small, okay, and here the high thermal conductivity materials can't be done, because high thermal conductivity material, by then the heat is already propagated here, so the heat dissipation will not be taking place in a proper fashion here. So that's only the difference. So other than that, if you have any problem regarding this thermal conductivity and thickness issues here, then prefer alternating current high frequency. So this is the only option here, there is no any other alternative here. So because if you are unable to do either one of the extreme of this configurations, then there is no other option, you have to go for a middle option here. That's the case here, and this actually will suffice here regarding the understanding of basic concepts of this arc welding process. In this class, what we have done is, we have understood the concept of thermionic emission, then we have understood the concept of this power source, then we have understood the concept of the temperature, then we have understood the concept of Lorenz forces, then we have understood the concept of heat generation, then we have understood the concept of the temperature also here. So these are the much picture regarding this in today's class regarding the arc welding process and its basics. I hope you understood. Thank you.